Good morning, everyone. This is the second lecture on the topic optoelectronic materials and devices. In this lecture, we'll be covering optical processes in semiconductors. I'll talk about what are the basic properties of semiconductors, what are the optical processes such as reflection, refraction, optical absorption, and the basic methods of distinguishing between direct and indirect bandgap semiconductors. In the first talk, I discussed about various types of semiconductors, and in this periodic table of elements, you see that the most common semiconductors are group 4 semiconductors, which are silicon and germanium, and the 3,5 compounds, which are most often used in optoelectronics, are materials like gallium arsenide, indium phosphide, gallium phosphide, indium antimonide, and indium arsenide. So this, in a nutshell, depicts the most important semiconductors that are used in optoelectronics. Now, what are the optical processes that are of importance in semiconductors? Now, if we have a ray of light incident at a semiconductor metal semiconductor air interface, we have various phenomena taking part. We have the incident beam being partly reflected and partly transmitted. The transmitted beam consists of portions which are absorbed and portions which are scattered. We'll discuss the various processes of absorption in a semiconductor in detail subsequently. Let us take the simple case of a reflection at the interface. As is well known, reflection at a interface obeys Snell's law. So if you have light going from a medium N1 to a medium N2, then Snell's law says that N1 sine theta 1 is equal to N2 sine theta 2. Here N1 is the semiconductor and N2 is air. One of the phenomena that take place in a interface is that if the angle theta 1 is equal to or greater than a critical angle theta c, then theta 2 is equal to 90 degrees. And as a result, we have the phenomena of total internal reflection, which is given by the condition N1 sine theta c is equal to N2, and therefore theta c, the critical angle, is sine inverse N2 by N1. Now, in the case of air, N2 is 1, so theta c is sine inverse 1 by N1. Let us take a couple of examples. For glass, N1 is 1.5, so the critical angle is 41.8 degrees. But in a semiconductor such as gallium arsenide, N1 is much larger. It is about 3.25, and as a result, critical angle is only 17.9. So as a result, we find that when light is going from a semiconductor into air, there is only a very small angle of light which can be emitted into the air. Any light coming at an angle greater than, say, 17.9 will be subject to total internal reflection. This is very important in the case of light-emitting diodes, where light is generated in the semiconductor and has to be emitted into air. So there's only a small cone of radiation that can enter air from a semiconductor. Now, if we look at the phenomena of reflection again, we know that the total amount of light reflected plus the total amount transmitted must be equal to the incident radiation. What is the amount of light reflected? Now, that is well known again from laws of optics, and we know that the percentage reflected is given by n minus 1 squared plus k squared over n plus 1 squared plus k squared, where n is the refractive index, k is defined as the extinction coefficient, and the complex refractive index n bar is equal to n minus ik. We shall see that the extinction coefficient k is related to alpha, the absorption coefficient. Now, take the case when k is equal to 0, then we have the condition that the percentage of light reflected, or the power reflected, is just n minus 1 over n plus 1 whole squared. This is a very important relation. Which tells us that for n is equal to, say, 3.25, R, as in the case of gallium arsenide, R is almost 30%. So we find that when light is incident from air going into a semiconductor, only about 30% of the light is directly reflected. This expression is valid at normal incidence, where the light is incident at 90 degrees to the planar surface. We'll see later on as to how the reflection, this reflection R, can be reduced by various techniques, such as that is valid for Yes, the question is, we are considering light incident with theta is equal to 0. Okay, for theta equal to 0, this expression is exactly valid. If theta is not equal to 0, obviously sine theta will come into this expression. And what I have assumed in going from here to here is that k, the extinction coefficient, is equal to 0. That means alpha is equal to 0. That means the material is totally transparent. Okay, totally transparent. Is that clear? And in this case, the n bar is the complex refractive index, which is equal to n minus ik. N is a real number, and k is a real number, and this is a complex refractive index. Right. Let us come to now mechanisms of absorption in a semiconductor. A typical semiconductor such as silicon or gallium arsenide is distinguished by having two energy bands. We have a conduction band and a valence band, which is separated by a band gap. A band gap is what distinguishes a semiconductor from a metal. In the case of an insulator, the band gap is much larger, of the order of 4 or 5 electron volts. In the case of a semiconductor, typically silicon, the band gap is 1.12 electron volts. Whereas for gallium arsenide, the band gap is 1.42 electron volts. Now, in this graph, what is plotted is energy in the vertical axis, and k, the wave vector, which is also proportional to the momentum. P is equal to h cross k, the momentum of the electrons on the x-axis. K equal to 0 is the center of the Brillouin zone, and we go from k equal to 0 towards the 1, 0, 0 direction on the right, and towards the 1, 1, 1 direction on the left. The green curve gives the energy bands, the conduction band and the valence band, and as I mentioned, it's separated by a band gap. One of the most important things to notice in these diagrams is that the conduction band minimum in silicon is displaced from the k equal to 0 point. So the conduction band minimum is displaced towards the 1, 0, 0 direction, whereas the valence band maximum is at k equal to 0. So this is what is known as an indirect gap semiconductor. Whereas for gallium arsenide, the conduction band minimum and the valence band maximum, they are both at k equal to 0. So this is a direct band gap semiconductor. So under thermal equilibrium, under normal temperature 300 degrees K, we find that electrons are located in the lowest energy position of the conduction band, and holes are located at the highest of the valence band, or as we know that the hole energy increases downwards, so this is the lowest hole energy and this is the lowest electron energy. Now when light is incident on these semiconductors, what happens? An electron can be excited from a valence band to a conduction band position, both in the case of a direct gap semiconductor or in the case of an indirect gap semiconductor. However, as you know, that such energy absorption processes involve both the conservation of energy and conservation of momentum. And notice here that the momentum of the electron is not the same as the momentum of a hole. Here, the electrons and the holes have the same value of k, so there can be conservation of momentum by a direct transition. Here, there is non-conservation of momentum by a direct transition, and some other entities, lattice vibrations, have to come into play. So, the most elementary process that occurs when light is incident on a semiconductor is excitation of electrons from the valence band to the conduction band, and the absorption at which this occurs, the wavelength at which this occurs, is given by the very simple relation the energy of the photon is equal to h nu, and this must be equal to Eg, the band gap of the semiconductor. Now we know that h nu can be written as hc by lambda is equal to Eg, and if we put in the right values of h and c, we get the relation that Eg in electron volts is equal to 1.24 by lambda in microns. So this is a very important relation that relates the energy of the incoming photons, or the wavelength of the incoming photons, to the band gap of a semiconductor. Now, as we saw in this energy band diagram, for silicon, the band gap is 1.12 eV, so the direct absorption edge is given by 1 point for silicon, lambda c is equal to 1.24 divided by 1.12, that is about 1.1 microns, whereas for gallium arsenide, lambda c is equal to 1.24 divided by the band gap, which is 1.42 eV, which makes it about 0.82 microns. So for any semiconductor, the fundamental absorption starts at an energy which is just equal to the band gap of the semiconductor. Now, what are the other processes that take place when light is incident on a semiconductor? Now, if we cover a wide expanse of energy, on the x-axis we have the photon energy, And on the y-axis, we have alpha, which is the absorption coefficient. We find that the fundamental absorption edge is here, near the band gap of the semiconductor. We have very strong absorption near, just above the band gap of the semiconductor. Just below the band gap of a semiconductor, the absorption coefficient is extremely small, and a semiconductor is extremely transparent. The value of absorption coefficient can be much less than even 1, and semiconductor is essentially a filter. Now, as we reduce the energy or increase the wavelength, notice that wavelength microns increase in this direction. The photon energy increases in this direction. As we go towards the infrared, the absorption increases slowly, which is due to absorption by free carriers. Thereafter, we get a very strong peak again in the infrared, which is called Reststrahlen, from the German residual rays. This is due to absorption by lattice vibrations or phonons. So we have phonon bands here at a distinct wavelength, and thereafter the optical absorption decreases, and we have peaks due to impurity absorption. Thereafter, there are certain absorption bands due to magnetic fields called magnetoabsorption. And finally, we have very long wavelengths. We have cyclotron resonance. Both these are absorptions that occur when a magnetic field is also applied. So if we use the conversion from energy into wavelength, we notice that this 1 eV corresponds to 1.2 microns. This is 12 microns. This is 120 microns, and this is 1,200 microns in the infrared. And here we go to, this is 0.12 microns in the UV, and this is 0.012 microns in the far UV. So this energy axis scans a large wavelength region right from the UV to the visible, into the infrared and the far infrared. And so far we have only discussed this fundamental absorption. that occurs due to excitation of electrons from the valence band into the conduction band. Now, alpha is a very important parameter here, the absorption coefficient, and let us see what that consists of. If we have a sample of thickness x, the incident light intensity is I0, the transmitted light intensity is I, then we know that I is equal to I0 e to the power minus alpha x. This is the definition of the absorption coefficient, and if we rewrite this, we can say that alpha, which is a function of lambda, is equal to 1 by x log Have I made a mistake here? Is this expression correct?
Yes, sir.
Okay. What is this?
Sir, I0 by A.
What should it be?
I0
I0 by I, right? Is that correct?
Yes.
Okay. So, experimentally, how is alpha determined? Alpha is determined experimentally by measuring this ratio of I0 by I, knowing the thickness x, and using this formula, which gives you alpha in, if x is in centimeters, this is obviously in centimeters inverse. Obviously, if the material is very highly, very strongly absorbing, then I will be much less than I0. Then this will be a large factor, okay, and therefore alpha will have a large value. From this, one can distinguish between materials which are strongly absorbing and which are not so strongly absorbing. For example, what is the absorption depth? Characteristic depth at which the intensity of the light becomes 1 by E of the incident radiation. Now, you can see that the absorption depth xd will be equal to 1 by because the absorption depth is defined as the depth at which I is equal to I0 e to the power minus 1, right? Or I by I0 is 1 by E. So the absorption depth is an important parameter. If alpha is very large, then the absorption depth is small. If alpha is small, then the absorption depth is large. And remember, alpha is a strong function of lambda, as I've shown. So this is only valid at a particular wavelength. Suppose we consider, again, a comparison between silicon, for which at lambda is of the order of about 0.5 microns, alpha is of the order of 10 to the power 2 centimeter inverse, then xd is just 0.01 centimeters, or of the order of 100 microns. I've taken lambda in the middle of the visible, in the green region. This is important in the case of devices like solar cells, where we are trying to extract energy from radiation. For the case of gallium arsenide, at lambda is 0.5 microns. Alpha, as we'll show through calculations, is of the order of 10 to the power 4 centimeter inverse. Therefore, xd in this case is 10 to the power minus 4 centimeters, or only 1 micron. So you notice that there is a tremendous difference between the absorption depth x at which radiation is absorbed in gallium arsenide and in silicon. The question that naturally arises is, why is this so? As I've mentioned earlier, silicon is a indirect gap semiconductor, and gallium arsenide is a direct gap semiconductor. So one has to calculate the optical absorption coefficient alpha for direct and for indirect gap semiconductors, which I shall do in the following lecture. Now, in order to calculate the direct fundamental absorption coefficients, we need to look at the band structure of a semiconductor, where electrons exist in the conduction band and holes exist in the valence band. Assuming parabolic energy bands, we know that we can write the energy of the electrons in the conduction band as p squared by twice m star E, where m star E is the effective mass of electrons in the conduction band. And if we take Eg as a band gap, and the reference of energy is at the top of the valence band, then this is equal to Pm squared by 2m E star plus Eg. We know that P is equal to H cross K, so we have H cross squared K squared by twice Me star plus Eg. Similarly, for holes in the valence band, we have a relation E will be equal to minus H squared K squared by twice MH star, where Me star is the effective mass of electrons, and MH star is the effective mass of holes. These are given as a ratio of the effective mass to that of the free electron, the effective mass of the free electrons. Right. Now, in order to calculate alphas, this is the first step. We have shown how the energy of the electrons varies as a function of K. Now, we have to find out now how many electrons are there in the valence band and how many electrons are there in the conduction band, because we are thinking of a radiation coming in, E is equal to h nu, which is exciting electrons from the valence band to the conduction band. So, at the outset, we can say that the absorption coefficient alpha is going to be proportional to the density of electrons available in the valence band, density of empty states in the conduction band. So if we have the electrons initially here in the valence band, suppose density is Ni, there are empty states Nf, and the transition probability is PIF. So the absorption coefficient is proportional to Ni transition probability PIF into NF. So we have to calculate what NIs are, what NFs are, and then take the known values of PIF in order to calculate the absorption coefficient. So the first step in this procedure is to look at what is known as the density of states or DOS. of electrons between energies E and E plus dE. We can describe these electrons as occupying a volume in momentum space given by Kx, Ky, and Kz, and these circles depict constant energy surfaces E and E plus dE. We want to find out how many such states are there NE in this annular space having a difference of energy dE. We want to calculate NE dE. Now, looking at these spheres of constant energy in momentum space, we know that the surface area of the sphere is 4 pi k squared, and therefore the volume in this annular space, volume of k space between the spheres of energy E and E plus dE is 4 pi k squared dk. We know that a single state, single electron state, occupies a volume in momentum space of 8 pi cubed by V, where V is the volume of the crystal. We also know that corresponding to each energy state, there can be 2 electrons of opposite spin. Hence, the number of electrons, number of energy states in the energy space between E and E plus dE is 4 pi k squared dk over 8 pi squared by V multiplied by the factor of 2 for 2 electron spins. If we take V is equal to 1 for simplicity, then this number of energy states comes to 8 pi k squared dk over 2 pi cubed, or if we rewrite this, NE dE is equal to 1 by 2 pi squared h cross cubed two m star to the power 3 by 2 e to the power half dE. here we have used the relation between E and K. E is equal to h squared k squared by twice me star. So we come to a very important relation. The density of states Ne dE is proportional to twice m star 3 by 2 e to the power half